Last week, we talked about measurement, about the gap between constructs and operationalizations, about reliability and validity, about the different levels of measurement. So we talked about the fundamental challenge of trying to capture something abstract with something concrete, right? So today we're going to start talking about what you do once you have measurements. So you've collected data, you have numbers, maybe hundreds or thousands of numbers, test scores, reaction times, income figures, symptom ratings, survey responses. Okay, so now what? Here's the problem. Human beings can't comprehend 500 separate numbers, right? We can't hold them all in our mind at once. Our eyes glaze over and the information just becomes noise. We need to do something to make sense of it. We need to summarize. We need to reduce that pile of numbers to something manageable, to a few values that capture what the whole pile presents or represents, I guess you could say. And the first question we typically ask is, what is typical? Where does the distribution sit? What's the center? I'll explain this to you. But, these are simple questions, or they seem like simple questions. Like there should be an obvious answer. You find the data, you find the middle, you report it. Done. But it's not that simple, okay? There are multiple ways to define typical, okay? They give different answers, and each one captures something different about your data. And it's something real about your data, but also hides something about your data. And so this matters beyond technique. It matters because people use statistics to mislead. They choose whichever average supports their argument. They report technically accurate numbers, but they're misleading. And if you don't understand the differences between measures of central tendency, you'll be fooled, or you'll fool other people, okay, repeatedly. Understanding which measure to use and when is protection against deception. It's statistical literacy in the most practical sense. Before we dive into central tendency, let me frame where we are in the course. So when you have a distribution of data, there are two fundamental questions you need to answer. Question one, where is the data centered? What is the center of the data? This is central tendency, what we're covering today. Question two is how spread out is the data? That's variability, which we'll cover in the next topic. Both questions are essential. So central tendency alone gives you an incomplete picture, but you have to start somewhere, and the center is the natural place to begin. So we're still in descriptive statistics. We're not making inferences about populations yet. We are just describing, okay? What does this sample look like? These concepts are the foundation for everything that comes later, okay? Let me start with a conceptual question. What does center mean? What does that even mean? Imagine you have a distribution of values spread along a number line. Okay, some values are low, some are high, they cluster in various ways. The center is supposed to capture where this distribution sits, where the mass lies, where a typical observation falls. But here's the problem. Center is ambiguous. It can mean multiple different things, okay? So let me give you 3 different ways to think about the center of a distribution. Okay, first, the balance point. Imagine the distribution as weights placed along a number line, and the center is where it would balance if it was placed on a fulcrum. Okay, this is what the mean captures, the average captures. Every value contributes to where the balance point sits. Move any value and you move the balance point. Second, the middle value. The center is the point with half the distribution above it and half below it. This is what the median captures. It doesn't matter how far the extreme values are, just how many are above and how many are below. Third, the most common value. The center is where observations cluster most densely, the peak of the distribution, where the most are. This is what the mode captures. It's a frequentist approach. What values shows up most often? So these 3 conceptions often give similar answers. If your data is symmetric, well-behaved, the mean, the median, the mode will be all close together. And it won't matter much which one you use. But sometimes they diverge dramatically. So in a skewed distribution, in data with outliers and bimodal distributions, we'll talk about all these, the 3 measures can give very different answers. And when they diverge, that divergence is informative, okay? It tells you something important about your data. Let's start with the mean, because it's what most people think of when they hear average, okay? The mean is the arithmetic average. You add up all the values and you divide by how many values you have. So the formula is simple. Mean equals the sum of all of the values divided by the total of values in. So where sum of x is the sum of all values and n is the number of values. We use different symbols depending on whether we're talking about a sample or a population. So for a sample mean, we write x bar. For a population mean, we write the Greek letter mu. So the calculation is straightforward. Add up all the values. This gives you the sum of x. Step 2 is count how many values you have. This gives you n. Step 3 is divide the sum by the count. Okay, and that's it. That's how you calculate a mean. Okay, so let's go through an example. Let me walk you through a concrete example step by step. So suppose you collected anxiety ratings from 8 patients on a scale of 0 to 8. So you have 5, 7, 3, 8, 6, 4, 7, and 8. Okay. So add up all the values. 5 plus 7 plus 3 plus 8 plus 6 plus 4 plus 7 plus 8. That equals 48. So the sum of x equals 48. Divide the sum by the count, or count how many values there are, right? There's 8 patients, and then divide the sum by the count. 48 divided by 8 equals 6. Okay, so notice that 6 is right in the middle of our 0 to 10 scale. And if you look at the data, most values also cluster around that region. So the mean seems like a reasonable summary. Okay, but I want you to understand what the mean represents, not just how to calculate it. Okay, so think of your data as weights placed along a number line. Okay, each observation is a weight sitting at its value. So if you place this setup on a fulcrum, the mean is where it would balance perfectly. Okay, wherever that fulcrum is. Oh, I can't find it. All right, so anyhow, picture a seesaw, right? You've got a seesaw. So your data points are objects placed along the seesaw at different positions, okay, corresponding to their values. So the mean is the point where the seesaw balances, okay? So the balance point would be the mean. So where the total weight on the left exactly equals the total weight on the right, okay? This is the geometric interpretation, and it has important implications. Mathematically, this balance property means that the sum of deviations from the mean equals 0. So if you take each score, subtract the mean, and add up all those deviations, you get exactly 0. Okay, so the positive deviations above the mean exactly cancel the negative deviations below. So let me show you with our anxiety data. So the mean was 6, right? So patient 1, you've got 5 minus 6, okay? That's -1. Patient 2, 7 minus 6, that leaves you with a +1. Patient 3, 3 minus 6 is a -3. Patient 4, 8 minus the deviation, the average of 6 is a deviation of +2. 6 minus 6, there's no deviation at all, so that's 0. 4 minus 6, that's -2, so deviation of -2. 7 minus 6 is deviation of +1, it's +1 above the average. 8 minus 6 is +2 above the average. So if you sum up all of the deviations, -1 plus -3 plus 2 plus 0 plus -2 plus 1 plus 2, anyhow, those all equal 0, okay? The deviations cancel perfectly. So this always happens with the mean. It's what makes it the balance point, okay? The strength of this is that it uses all information because the mean is the balance point. Every single value in your data set affects it. Nothing is ignored, okay? Move any value and you move the mean. Okay? When you're trying to summarize an entire distribution, this is a good thing. You want a summary that takes everything into account. The mean does that, okay? This property also gives the mean nice mathematical properties, okay? It plays well with other statistical procedures. It's the foundation for many of the techniques that we're going to learn later on in this course, okay? But there is a problem. There's a weakness. So because every value affects the mean, a single extreme value can drag the mean far from where most of the data lies. So one unusual observation can distort your summary of hundreds of typical ones, okay? Let me give you an example that'll make this vivid. So a classic example is the billionaire in the room, okay? So imagine you've got 5 people in a room, okay, with annual incomes of like 30,000. You've got somebody else with 35,000, 45,000, and a 5th guy with 50,000. So what's the mean income? Okay, so you add all of these up, okay? And so 30,000 plus 35 plus 45 plus 50, that all equals 200,000, okay? And then step 2 is count how many total values there are. So there's 5, right? 1, 2, 3, 4, 5. And so then you'll divide the 200,000 by the total values, that's 5. And what does that equal? 200,000 divided by 5 is 40,000. Okay, so the mean is 40,000. And look at every single person's income in here. It's all within $10,000 of that mean. So the mean sits right in the middle of the range, and it seems like a perfectly reasonable summary. Okay, now imagine Jeff Bezos walks into the room. Bezos's annual outcome is, I don't know, approximately $10 billion. Not his wealth, okay, his income. So then what's the new mean? So now you have to sum all this up. $200,000 plus 10 billion equals 10,200,000 divided by the new total, which is now 6 because he walked into the room. So 10,200,000 divided by 6 is like $1.6 billion. Okay. So the mean income in the room is now approximately $1.6 billion. Think about what just happened. 5 people still earn between $30,000 and $50,000 per year. One person earns $10 billion. And the mean says the typical income of this room is 1.6 billion. No one in the room is anywhere close to the typical income. Okay? The 5 regular people earn about $40,000, which is roughly 0.02% of the mean. Bezos earns 10 billion, about 600% of the mean. The mean describes nobody. The mean told the truth mathematically. The balance point of that distribution really is around 1.67 billion, but the mean told a lie. Okay, substantively. It completely misrepresented what a typical person in that room earns. Okay, so this is the crucial insight. The mean is the balance point, not necessarily where most of the data are. Okay, so when extreme values are present on one side of the distribution or the other, they shift the balance point dramatically toward that extreme value, what we call an outlier. Okay, let me give you another example to reinforce this point. So suppose 10 students took an exam and they got these scores. So 72, 75, 78, 80, 82, 83, 85, 87, 88, and 90. Okay. So when we calculate the mean, you're going to sum all of these up. Okay. And I'll just do that for you. So that total is 820. Okay. That's the sum of X, right? How many values are there? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Okay, so 10 values. So you take the sum of X, 820, divided by 10, divided by N, right? Which equals, okay, the average, the mean. So the mean is 82, okay? And all students scored between 72 and 90. That was the range. Okay. Everyone is within 10 points of the mean. So that's reasonable. That's a reasonable deviation. Now, suppose one student was absent and takes a makeup exam while sick, and they only get a score of 15. So add 15 points to that. So now the new sum is 835, okay, divided by now 11. So the new average is 75.9. The average dropped from 82 to 76. One struggling student pulled the entire class average down by 6 points. Is 76 a good summary of this class? Not really. 10 students scored between 72 and 90. One scored 15. The mean of 76 suggests typical performance is worse than what 10 out of 11 students actually achieved. Okay. So let me summarize the key properties of the mean. The mean includes every score. Every value contributes, which means extreme values pull the mean toward them. Outliers pull the mean toward them. The mean can be a non-integer, so even when all your data are in integers, the mean of like 7, 8, 8, and 7 is 7.5. It's a value that doesn't appear in your data, and that's fine. Okay, the mean doesn't have to be an actual data point. It represents the center, not a specific observation, not a specific data point that you collected. So the sum of deviations from the mean equals 0 every single time. Positive deviations exactly cancel out negative deviations, and this is what makes it a balance point. The mean is sensitive to every value in the distribution, so change any value and the mean changes. And this is both a strength in that it uses all information, as well as a weakness. Outliers have disproportionate influence. Okay. The mean is appropriate to use when you have interval or ratio level data. The mean requires equal intervals to be meaningful, okay? You have to have equal intervals. You can't compute a meaningful mean from nominal or ordinal data, okay? So remember our discussion from last time about levels of measurement. Your distribution is, so let's say, reasonably symmetric. It's not heavily skewed. You have no extreme outliers, or the outliers are genuine observations that you do want to include, okay? You want to use all the information in your data when every value should count. Okay, that is when you use the mean. The mean can be misleading when your distribution is skewed. Okay, the mean will get pulled towards the tail of the skew, and we're going to talk more about skews later. So outliers are present. This is when means can be misleading. Extreme values distort the mean. So you have ordinal data. Computing the mean of Likert scales is problematic, right? Because the intervals aren't equal. If you rate satisfaction from 1 to 5, the psychological distance from strongly disagree to disagree may not be, equal, agree to strongly agree. And the mean assumes that intervals are equal. And in this case, they're not. Okay, so that's a problem. If the mean doesn't represent the typical experience, when almost nobody is near the mean because the distribution is bimodal or heavily skewed or something, you don't want to use the mean. Okay. All right, so now let's talk about the median, okay, which takes a completely different approach to finding the center. So if the mean is not appropriate to use, the median might be. So the median is the middle value when all values are ordered from lowest to highest. It's literally the value in the middle, the 50th percentile. Half the observations are above it, half are below. The median doesn't care about how far values are from the center if there's outliers, just about the position. This is what makes it resistant to outliers. Okay, so let's talk about how to calculate the median. To find the median, you have to follow these steps. So step 1 is arrange the values from lowest to highest. Step 2, find the position of the median, preferably using a formula, okay? This formula makes it much easier to calculate. So the median is in the total number of values plus 1, okay, divided by 2, okay? And then look up the value that's at that position. So this is calculating the position of the number that you are going to find that equals the median, okay? So if the position is a whole number, that's your median. If it's a decimal, like 5.5, then you average the two values on either side. Okay, so this helps you to find the position. And the way I think about it is, it's easier if you think 1 plus n, okay, because this is the range. Okay, you've got one value all the way to whatever the total amount of your values are. And then you're going to find the middle. Okay, you're going to have that. Okay, that's the divided by 2 part. Okay. So you take the range 1 to however many values you have and then divide by 2 to find what's in the middle, okay? So let's go through an example. Suppose you have 7 reaction times that you're measuring in milliseconds. So you have 340, 290, 310, 450, 280, 320, and 300, okay? So order those from lowest to highest. So now you have 280, 290, 300, 310, 320, what's the next one? 40, and 450, okay? So now you have to find the position that you're going to, where's the middle? So the total, there are 7 things. So n equals 7, okay? So then you're doing the range 1 all the way to 7, first position to 7 position, and then you're going to have it, you're going to find the middle, okay? So obviously that's 8, okay? 8 divided by 2 equals 4. Position 4 is what we're looking for, okay? So some of you might be looking at that formula and wondering, where does the plus 1 come from? Why isn't it just n divided by 2? And this is worth understanding, right? Don't just memorize formulas, understand why they work, okay? We count positions starting at 1, not 0. The first value is position 1, okay? The second value is position 2, and so on. So what's the middle position? It's the average of the first position and the last position, okay? 1 all the way to the n. First position is 1, last position is whatever, n, okay? So then you average the first and the last. 1 to n divided by 2. That's where the formula comes from. And the plus 1 is because we're starting count at position 1. So if you look at our example, we have 7 values, position 1 through 7. What's the middle? The average of 1 and 7, okay? 1 plus 7 divided by 2 is 8 divided by 2 equals 4, okay? So position 4, like I said, is the middle. And if you count, positions 1, 2, 3 are below it, positions 5, 6, 7 are above it, okay? 3 on each side. So when you understand why a formula works, you don't have to memorize it, you can reconstruct it. And if you make an error, you can catch it because you know what the answer should look like. So try to never just memorize, try to understand. Okay, so step 3, we're going to look up the value at the position. So position 1 is 280, position 2 is 290, position 3 is 300, and position 4 is 310. Okay, this is the median. 320 would be position 5, 340 would be position 6, 450 would be position 7. Okay, so position 4, that's what we came up with the formula, that's the middle of the positions. Position 4 equates to this position here, 310 milliseconds. The median is 310 milliseconds. So notice there are exactly 3 values below 310, 280, 290, 300, and exactly 3 values above 320, 340, 450. The median is right in the middle, okay? Let's go through one more example where that was looking at an odd number of values. This is an even number of values. So suppose you have 10 dream counts. How many dreams did a group of people have over the last week or something? So you've got 7, 8, 8, 7, 3, 1, 6, 9, 3, 8. You're going to order those from lowest to highest. So 1, 3, 3, 6, 7, 7, 8, 8, 8, 9. Okay. Step 2 is find the position. So what's the in? What are the total values? 10. Okay. So you're going to start from position 1 and then all the way to position 10. Okay. 1 plus 10, and then you're going to average that. You're going to take the average of the position by dividing by 2. So you take the whole position and you have it. Okay, you find where the half point mark is. That's the divided by 2 part. Okay, so 1 plus 10 is 11, divided by 2 equals, 5.5. So position 5.5, okay? So we need the values at position 5 and position 6, and then we average them. So that's right here, okay? So position 5 is 7, position 6 is 7. So the way you average those, obviously, or hopefully obviously, because you did the mean already, 7 plus 7. So the sum of the values divided by the total number of values, which is just 2, equals, 7. Hopefully that was easy for you. If not, go back and review mean, because that should be easy at this point. Okay, so the median number of dreams remembered was 7. Okay, that's the median. So if it's even, you have to take 2 numbers and average those out. So there's one extra step. Okay, but that should be pretty easy to figure out. All right, now let me show you why the median matters. Let's see what happens when we introduce an outlier. So we have the original data, okay? We've got it ordered. So let's calculate both the mean and the median, okay? So the mean, if we add all of these up, 1 plus 3 plus 6 plus 7 plus 8 plus 9, that equals 60, okay? So all of these together, I'm just going to put it right here, the sum of the totals equals 60, okay? And then there's 10 values, so 60 divided by 10 equals 6. That's the mean, okay? The median, the position 5.5 position, the values are 7 and 7, so the median equals 7, okay? That's the median. Now, suppose one person misremembered and actually recalled 100 dreams instead of 8, okay? So now you have 1, 3, 3, 6, 7, 7, 8, 8, 9, and then you've got a 100 in here, okay? So now the new mean, the sum is, and let's just drop one of these, okay? So the new sum would be 152, okay? Let me just go to a new page. 152. That's the new total. Okay, 152 divided by 10, because we dropped one of the numbers, equals 15.2. That's the new average, okay? The new median, the position is still 5.5. Position 5 is still 7. Position 6 is still 7. The median is still 7, okay? So the mean jumped from 6 all the way up to 15.2 just because one person had so many dreams during that week. It more than doubled. But the mean stayed exactly at 7. It was unchanged. So even though there's this huge outlier, the median doesn't change at all. The mean, however, the average is very sensitive to outliers, and it changed dramatically. Okay, and this is a key difference. The median only cares about position. It doesn't care about the magnitude. It doesn't matter whether the highest value is 9 or 100 or a million. The median just asks which value is in the middle position. The mean, by contrast, incorporates every value's magnitude into its calculation, so it's very sensitive to those outliers. Okay. So the median only depends on position, not value magnitude. So extreme values doesn't affect it. Okay, this makes the median more stable when those outliers are present. Doesn't use all the information. Okay, that's however. So that is the flip side. The median ignores the actual values of observation and only uses the position value. Okay, so pros and cons. Two distributions can have the same mean despite being very different in their extremes. Okay, so the distributions of 1, 6, 7, 9 can have and 1, 6, 7, 100 have the same median but very different spreads. Okay, or 1, 6, 7 million has the same median but they're very different spreads. So it's appropriate for ordinal data. Okay, that's something to remember. This is crucial. The median doesn't require equal intervals. It only requires that values can be ordered. You can compute a median for a Likert scale responses without assuming the intervals are equal. That's not important. So strongly agree is above neutral. That's all you need. Okay. You don't need to assume that the psychological distance between categories is the same. Okay, which, as we talked about earlier, is an issue for other things. Okay. Like the mean, the median can fall between two values. Okay, so it doesn't have to be an actual value that you've collected. When you have an even number of observations, not the odd, okay, a median of 7.5 might not appear in your actual data, and that's fine. It still represents the center. Okay. Let's talk about when to use the median. So the median is appropriate when, like I said, you have ordinal data, Likert scales, rankings, ordered categories. Okay, those are all okay. The median doesn't assume equal intervals. Your distribution can be skewed. Okay, the mean would be pulled towards the outliers. Okay, if outliers are present, you want a center that's unaffected by the extreme value, so the median might be more appropriate. The middle value is most representative. The median better captures what typical means in your data collection. All right, why does this matter? This is why you almost always see median household income reported rather than mean household income reported. Income distributions are heavily right skewed. Most people earn moderate incomes, maybe $40,000 to $80,000, but a small number of people earn enormous amounts, millions or billions of dollars. Okay, if you compute the mean income, the average income, those millionaires and billionaires pull it up dramatically. The mean might be 85,000 when most families earn 50 to 60,000. So the median gives you the income where half of the households earn more and half earns less. It represents what a typical family actually experiences. Okay. And this has policy implications, right? If a politician reports rising mean incomes as evidence of economic progress, but median income hasn't budged, that means all the gains went to the wealthy, even though it makes it look like everybody is making more money. Typical families aren't better off at all in this scenario. The mean is technically accurate, but substantively it's misleading. This isn't an abstract concern. This is how people get deceived about the state of the economy and whether it's getting better or worse. Okay, so understanding the difference between mean and median is essential for something like informed citizenship. The third measure of central tendency is the mode. It's the simplest conceptually, but the most limited in many ways. Okay, so you don't see it used all that often. The mode is the most frequently occurring value. Which value appears most often? That's it. No formula needed. You just count frequencies and find the value that appears the most frequently. The mode is the only measure of central tendency that works with nominal data, okay, categories without any inherent order to them. Okay, so how do we find it? Step 1, count how many times each value appears. Step 2, identify which value appears the most frequently. Step 3, that value is your mode. Okay, pretty simple. So let's look at our dream example. Okay, so what was that again? That was 7, 8, 8, 7, 3, 1, 6, 9, 3, 8. Okay, So count the frequencies. Now in this one, it doesn't matter whether it's in order or not, like we did for the median, it has to be in order. Mean and mode, it doesn't, okay? So value number 1, okay, appears, let's see, 1 appears 1 time, okay? 3 appears 2 times. 6 appears 1 time. 7 appears 2 times. 8 appears 1, 2, 3 times, and 9 appears once, okay? Which one appears most frequently? Obviously, that is 8, okay? It's really simple. It's not difficult to do. The mode is the simplest thing you're going to do in statistics, okay? So the mode is 8. It appears 3 times. That's more than any other value, okay? So the interpretation for this is the most common number of dreams remembered was 8. The mode really shines with categorical data, where mean and median are meaningless. You can't use those for categorical data. So suppose you surveyed 50 patients about their primary diagnosis. Let's say depression, there's 18 patients. Actually, let's write this down, okay? So you have depression, there's 18 patients. Anxiety, you have 15 patients. PTSD, you have 8 patients. Bipolar, you have 5. And just other random diagnoses, you have 4. Okay, what's the mode? See if you can answer that. Okay, it's the most common diagnosis. What's the most common diagnosis? Depression. Okay, you can't compute, you can't calculate, you can't compute a mean diagnosis. You can't say what the average diagnosis is, okay? You can't order diagnoses on a number line. They don't have values. They don't have intervals, okay? But you can identify the most frequent category, the most common category. That's what the mode does. So the mode of this is 18, okay? Depression is the most common diagnoses, okay? So the mode is always an actual value in your data, unlike the mean or the median. The mode can't fall between values. So it has to be something you actually observed. So this works with nominal data. You know, what's the most common eye color? Brown. What's the most common political affiliation? You're Democrat or Republican, depending on your sample. So you can find modes for categorical data where mean and median are impossible to do that for, okay? If all values occur with equal frequency, there's no mode. Okay, the distribution is uniform. Everything's exactly the same. If multiple values tie for the most frequent, you have multiple modes. Okay, 2 modes, that's what we call bimodal. More than 2 modes, we call multimodal. Okay, the mode ignores most of your data. So the mode only looks at frequency. It doesn't consider the magnitude of values in the data, 1, 1, 1, 1, or 100, 100, 100. The mode is 1. Okay, it appears 4 times. But that ignores that 100 appears almost as often and is dramatically higher in magnitude and value. Okay, so there's pros and cons like with every single one. So you have to look at your data and determine what's the best thing to use for what I'm researching. Okay, so the mode is most appropriate to use when you have nominal or categorical data. It's the only appropriate choice for those. Eye color diagnosis, political party, your favorite color, these require the mode. Okay, if you want a quick summary of what's most common, you use the mode. Okay, maybe you want to supplement the mean and the median with additional information. That would be appropriate to use the mode. If your distribution is bimodal, when there's 2 distinct peaks, 2 distinct modes, okay, most common things, the mode tells you an important story that the mean and the median would completely miss. So bimodal distributions, you might want to include the mode. Okay, maybe you include it along with the other ones, depending on what type of data you have, but it would definitely be something that would be interesting to include in your research. Okay, bimodal distributions. Let's talk about this more. So this is important. This is where central tendency can completely mislead you if you're not careful. Okay, so a bimodal distribution where there's 2 peaks, okay, it has 2 peaks. It has 2 values or regions where observations cluster most densely. Okay, in a bimodal distribution, the mean often falls right in between those 2 peaks in a valley where almost nobody actually is. There's no observations there. Okay, so it can be bimodal distributions with the average, the mean can be very misleading. Okay, suppose you're measuring depression scores in a clinical sample. Okay, let's go through another example. Scores range from let's say 0 to 50, okay? Severe depression. No depression to severe depression. So your data might look like this, where there's lots of scores around 10 to 15, okay, with mild symptoms. And then lots of scores again around 35 to 40 with severe symptoms, okay, with relatively few in between. That is what kind of distribution? Bimodal distribution, okay. Why is this going on with your scores? Because you've got two populations mixed together. You've got people with some adjustment issues who are mildly depressed, okay? And then you have people with major depressive disorder who are severely depressed. What is the mean? Maybe, 25, right? They're in the middle. But almost nobody scored 25 in your sample. That value represents neither population that's in your sample. The mean describes no one at all. So if you reported only the mean depression score, you'd completely miss the fact that your sample consists of two distinct groups that require totally different treatments. So let me give you another example that's even more dramatic. So class A takes an exam, and here are the scores, okay? If you add up all the scores, that's 774, divided by how many total scores there are, which there's 10 scores, that's 77.4. So everyone scores between 72 and 82. The mean of 77 represents the class pretty well, okay? So students are clustered together. Class B takes the same exam, okay? So this is for class B. And their scores are 45, 48, 50, 52, 55, and then they jump up to 95, 97, 98, 99, 100. Add all those together, that's 739, divided by how many total? 10 again, and that's 73.9. So that's pretty similar to the first class, but half of the class scored around 50 and half scored around 97. The mean of 74 doesn't represent anybody in that group, okay? So if you only saw the means 77 for class A and 74 for class B, you might think they're similar, with class A slightly higher. But class A is a homogeneous group, meaning that they're similar, they're moving together. Class B is a disaster, okay? Two completely separate populations. Half the students are excelling, half are failing. They need completely different interventions. They need to be taught in different ways. The mean hides this. The mean lies. This is why you should always look at your data, not just compute summary statistics. A histogram would reveal bimodality immediately. You'd see two peaks, but even without visualization, there's clues. You can compare the mean, the median, and the mode. In bimodal distributions, you might have two modes, okay? The mean and the median, usually they might fall between them. So look at the spread. Unusually high variability might indicate two populations are mixed together. If you think about your population, are there theoretical reasons to expect subgroups? Are there different ages, different severity levels, different underlying conditions? So the lesson is never trust a single summary statistic. Always visualize, always think about what your population actually looks like. Now let's think about how these measures relate to each other, because the relationship between the three tells you a lot about your data. So in our dream example, okay, you've got your data 7, 8, 8, 7, 3, 1, 6, 9, 3, 8. Okay, the mean was 6, the median was 7, and the mode was 8. So three different values, all claiming to represent the center of the same data. Now the question is, which one's right? And the answer is they're all right. Each captures something that's true about the center. They're just using different definitions of center. So the mean tells you that balance point where the distribution would balance on a fulcrum. The median tells you the middle position where half the data fall above and below. The mode tells you the most common value, the peak of the frequency distribution. The question isn't which one is correct, it's which one is the most useful for your purposes, okay? When they agree, usually you'll see this in symmetric distributions where the data are all evenly distributed around the center. Okay, the mean, the median, and the mode will be very close together. They'll all tell roughly the same story. Height data, for example, tends to be fairly symmetric. The mean height, the median height, the modal height, they'll all be similar numbers. It doesn't matter which one you report. This is the ideal case when the three measures agree. You can be confident that your summary is capturing something real about the center. When they diverge, though, which is usually in skewed distributions, the pattern of divergence tells you about the shape of your distribution, okay? So you won't have the same mean, mode, and median, okay? This is one of the most practically useful things you'll learn today, how to detect skewness by comparing the three measures. So this shape here, this bell curve, that is a symmetric skew. So a positive skew, a right skew, a distribution is positively skewed or right skewed when it has a long tail extending to the right towards higher values, okay? Picture a histogram, right? Okay, so most values cluster on the left, the lower end, but there's a long tail stretching toward the right where the unusual high values are. In a positively skewed distribution, the mode is the lowest. It sits where the values cluster most densely on the left. The median is in the middle, somewhat pulled to the right, but resistant to the extreme values. The mean is the highest, pulled most toward the right tail by the extreme high value. So you have a pattern here. Mode is less than median, which is less than mean, okay? So income is the classic example of positive skew. Most people earn moderate incomes. That's where the mode is, maybe around 40,000. Some people earn quite a bit more, and a few people earn enormous amounts, millions, tens of millions, billions. This creates a long right tail. The median might be around 60,000, okay, the point where half earn more and half earn less. But the mean might be 85,000, pulled up by the millionaires and billionaires. So if someone asks what's the typical income, the mode or median probably gives a better answer than the mean. Most people aren't earning anywhere close to the mean. A distribution is negatively skewed or left skewed when it has a long tail extending to the left toward lower values. Most values cluster on the right, the higher end, but there's a tail stretching towards unusually low values. In a negatively skewed distribution, the mean is the lowest. It's pulled most toward the left tail by the extreme low values. The median is in the middle, somewhat pulled left, but resistant to the extreme outliers. The mode is the highest. It sits where values cluster most densely, which is on the right. So the pattern is mean is less than median, which is less than mode. So here's an example. Imagine a test that most students found easy, okay? Most students scored well, lots of 85s, 90s, 95s. The mode might be around 90. But a few students struggled badly, scoring 30s or 40s. This creates a left tail. The median might be around 85, the middle score. The mean might be 82, pulled down by the low scores. Again, if you want to describe what's typical, the mode or median might be more representative than the mean. So here's the practical upshot. You can detect skewness without even looking at a graph. If mean equals median, which equals mode, your distribution is roughly symmetric. If mode is less than median and median is less than mean, your distribution is positively skewed with a right tail. If mean is less than median, which is less than mode, so the opposite, your distribution is negatively skewed with a left tail. So this is a quick diagnostic tool. Compare the three measures and you learn something about the shape of your distribution without having to do any math. So let me connect what we're discussing today back to what we covered last week about levels of measurement, because this connection is crucial. Okay. Not every measure of central tendency is appropriate for every type of data. The level of measurement determines which measure you can legitimately use. For nominal data, categories without order, the only appropriate measure is the mode. What's the most common eye color? What's the most frequent diagnosis? What political party has the most members? You cannot compute a mean or median for eye color. You can't order blue, brown, green on a number line. You can't say brown is higher than blue. The mean is meaningless. The median is meaningless. But you can count frequencies. You can identify the most common category. That's the mode. For ordinal data, categories with order but unequal intervals use the median or mode. Likert scales are the classic example. Strongly disagree, neutral, agree. There's an order, but the psychological distance between categories isn't necessarily equal. The median works because it only requires order. You can identify the middle category. The mode works because you can count frequencies. The mean is problematic. So remember, the mean assumes equal intervals. When you compute a mean Likert scale, you're treating the data as if the distance from strongly disagree to disagree is the same as the distance from agree to strongly agree. It probably isn't the same distance. Again, this is psychology's dirty little secret, right? Researchers routinely compute the means of Likert data anyways. Sometimes it works out, sometimes it doesn't, but you should be aware of the assumption that you're making. For interval data, equal intervals, no true zero, and then ratio data, which is equal intervals plus a true zero, all three measures are technically appropriate. So temperature, IQ scores, reaction times, income. You can compute mean, median, and mode for all of these. But technically appropriate doesn't mean equally useful. So you still need to consider distribution shape and the presence of outliers. So for skewed data like income, median is usually more appropriate than mean, even though both are technically legitimate. All right, so to summarize this, nominal data is mode only. Ordinal data, median is preferred, mode is also fine, but the mean is questionable. Interval and ratio data, all three are possible, and you choose based on the distribution shape and the purpose. So a computer will calculate anything you ask it to, okay? It will happily compute a mean eye color if you code blue equals 1, brown equals 2, green equals 3. That doesn't mean the result is meaningful. You have to know what's appropriate, okay? Now, sometimes when you want to do a mean, but you have these outliers, we do what's called a trimmed means. Okay, this is a compromise approach. So sometimes you want the mathematical properties of mean, but you're worried about those extreme values distorting the picture. Okay, so trimmed mean is the compromise. So a trimmed mean is calculated by first ranking the data from lowest to highest, then you remove a certain percentage from each end, and then compute the means of what's remaining. Okay, so a 10% trimmed mean, for example, means that you remove the bottom 10% and the top 10% of the values, then compute the mean of the middle 80. That gives you a more robust mean than the ordinary mean. It's less affected by the outliers, but while you're still using a lot more information than the median will use. Okay, so that's a trimmed mean. And you've seen trimmed means in action even if you didn't know the name. Like in gymnastics and diving competitions, for example, they throw out the highest and the lowest scores from the judges before they average them. So one judge who has like an abnormally high score, maybe because they're biased towards their own country's athletes, or a judge with an abnormally low score who maybe doesn't like the athlete personally, I don't know, for whatever reason, they'll be thrown out, and that won't distort the final result. So that is essentially a trimmed mean. You remove the extremes, you average what's left. You can also just throw out outliers. You can just decide to, just because you think that there's a reason for that, but you really have to justify it. And there's been a lot of problematic research that's done by people throwing out what they labeled as outliers. So there's an ethical question with that, okay? So you have to be transparent about what you do. You have to consider, checking whether your conclusions are sensitive to these things, whether they're really representing the truth. Like all summaries, it involves choices. Now I want to step back from the technical material, so no more math, and talk about something important, something that affects you as citizens, as consumers, as human beings, trying to understand the world. Mark Twain popularized the phrase lies, damned lies, and statistics. And the implication is that statistics are used to deceive. And it's true. It happens constantly, deliberately, and there's real consequences to it. But here's the thing. It's not the statistics that lie. It's the people using them. Guns don't kill people sort of thing. The numbers are usually accurate. The deception comes from the selective presentation, choosing whichever statistic supports the argument that you want to make. And the most common form of this sort of deception involves central tendency. People choose whichever average looks best for their argument. An example is, a company posts a job and says the average salary is $95,000. So that sounds great. You apply, you get hired, you start to work. Then you discover most employees actually make around $60,000. The CEO makes $5 million, and a few executives make like $500,000 or more. But the mean salary, it is indeed $95,000. The company didn't lie, but the typical employee like you earns far less. If they had reported median salary, you would have seen a number closer to 60. Much closer to what you'll actually earn, but that number doesn't look as good in a job posting. So this is a deliberate deception. It's technically accurate, it's substantially false. Another example is, a politician claims that the mean household income is rising, evidence of economic progress, but if you look closer, all the income gains went to the top 10%. The bottom 90% saw their incomes, stagnate or even decline. Median household income, what families typically earn, that barely budged. So the mean rose because the wealthy got wealthier, but most families weren't better off at all in this situation. So it's technically true the mean did rise, but practically it's false. Most people aren't better off. So the impression of this prosperity is, completely misleading. for this fictional statistic, by the way. Okay, here's another example. A drug company reports that patients showed a mean improvement in symptoms on their new medication, but the reality is that a few patients improved dramatically, their depression lifted, their pain disappeared, but most patients showed very little change, and some even got worse. So the distribution here might be bimodal, some responders and a lot of non-responders, or it might be highly skewed, a few miracle cures pulling up the mean. So it's technically true, mean improvement exists, but it's practically false. The typical patient experience is mediocre. So patients are misled about their probability of getting better. So in all these cases, the numbers are accurate. No one is technically lying. You could verify the calculations. The presentation is selective. They're choosing the statistic that looks best for their argument. And the context is missing. The distribution shape is hidden. Other measures aren't being reported, which leads to a false impression and the audience draws incorrect conclusions. So this is the technique, using correct math to create incorrect understanding. Now, let me be direct about something. This isn't just about technique. This is about ethics. When you choose which statistic to report, you're making a moral choice. You're deciding what picture of reality to present. You can present one that's accurate and representative, or one that serves your interests while misleading your audience. So the fact that the numbers are technically correct does not absolve you of guilt. If you report mean salary knowing that the median would give a more accurate picture of typical employee experience, you are being dishonest. The technical accuracy is camouflage for deception. Okay, so there's an obligation to choose the measure that honestly represents the typical experience, that tries to represent the truth. And when possible, you should report multiple measures and then let the reader judge for themselves. So you don't just do the mean, you also do the median and the mode, okay, as applicable. So this applies whether you're a company, a politician, a scientist, or a student writing a paper. The temptation to choose favorable statistics is universal, but the ethical requirement to resist that temptation is also universal, okay? So this is why statistical literacy matters. Not just for research methods and statistics, but for citizenship, for being a good citizen. When someone reports the average, ask which average, because the mean, the median, and the mode are all averages, okay? Is it the median? Is it the mode? What does the distribution look like? Is the reported average representative of the typical case, or is it being distorted by outliers? Okay. You should also look out for red flags. So if there's only one statistic reported, why? Why not show multiple measures? What might the other measures reveal that maybe they don't want you to know? If there's a defensive response to simple questions about distribution, honest people welcome scrutiny. If there's a refusal to show the actual data or visualizations, what's being hidden. Another red flag is vagueness about which measures were used. So average is ambiguous. It could mean any of the three. Why aren't they being specific? And both political sides do this, okay? Partisans of all stripes choose statistics supporting their narrative. So the skill you need is seeing through that selectiveness, asking the right questions regardless of who's making the claim. Okay? Statistical literacy is a civic virtue. Without it, you cannot evaluate claims about the economy, inequality, healthcare, education, any domain where data is used to argue for policies. You will be manipulated repeatedly. Now, I want to introduce a concept that's not exactly about central tendency, but is deeply related to how we interpret aggregate statistics. Okay, aggregate means you're taking everything and you're summarizing it, you're aggregating it. Okay, so these are summary statistics, aggregate statistics. So if you're looking at all of the individual data, what did people of this age score? What did the people of this race score? What did people of this gender score? That's disaggregated. It's in its parts. But you could combine the whole thing and now it's aggregated statistics, okay? And this thing I want to teach you now is called the ecological fallacy, okay? And we're almost done if you guys are getting a little tired. I promise we're getting there. So the ecological fallacy is the mistake of drawing conclusions about individuals from that group level aggregated data. The group pattern might be real, the aggregated pattern might be real, but applying it to individuals can be completely wrong because group averages don't tell you about individual variation. So let me give you an example. Here's a famous tongue-in-cheek example that's true, but illustrates the problem. It is a true fact that countries with higher average chocolate consumption have more Nobel Prize winners per capita. There's a genuine correlation at country level. Okay, Switzerland eats a lot of chocolate, for example, and has many Nobel laureates. Does this mean eating chocolate makes you more likely to win a Nobel Prize? Okay, obviously not. The correlation exists at the country level, not the individual level. Okay, so there's many Nobel Prize winners who don't eat chocolate. Okay, it's just they happen to be Swiss, and the Swiss happen to eat a lot of chocolate. So on the group level, that's true, but the individual people, no. Okay, it's not true. So what's actually going on? Wealthy countries consume more chocolate. It's a luxury good, and wealthy countries have better universities, better research infrastructure. Wealth causes both things. Chocolate's not doing anything. Okay. So this group pattern doesn't translate to individual causation. You can't answer individual level questions with group level data. It doesn't necessarily translate. Okay. So it can be a problem. Group averages can hide an enormous amount of individual variation. Okay. So how do you avoid it? You have to be aware of what level your data represents. So remember that group patterns don't determine individual patterns, and resist that temptation to extrapolate from the aggregate to the disaggregate, from the aggregate to the individuals. Okay? If you want to understand individuals, you need individual level data. There's no shortcut. Okay, so now I want to tell you about something that's even worse than the ecological fallacy, and this is the last big learning thing in this chapter, okay? It's called Simpson's paradox. In Simpson's paradox, the aggregate statistics don't just fail to capture the truth, they can tell you the exact opposite truth, okay? So let that sink in. The aggregate can literally reverse the conclusion. You look at the overall number and draw one conclusion, and then you look at the disaggregated data, and the truth is the opposite, okay? So here's an example. This is from the 1970s. This is true. UC Berkeley was accused of gender discrimination in graduate admissions, and the evidence was really damning. So the overall admission rates, 44% of male applicants were admitted, and only 35% of female applicants were admitted. That's a 9 percentage point gap. So it looked like clear discrimination against women. Lawyers got involved. Berkeley was facing some serious legal consequences. But then the researchers examined admissions department by department, and they found something shocking. So in most individual departments, women were admitted at equal or higher rates than men. So how is it possible? How were women being admitted into equal departments at higher rates than men, but not in the overall school? Okay, so here's what was happening. Women applied disproportionately to the most competitive departments: English, art, history, psychology, departments that rejected most applicants regardless of their gender. Men applied to less competitive departments: engineering, physical sciences, departments that accepted a higher percentage of applicants because they had more spots available and less people applying. So within each department, there was no discrimination. A woman who applied to the English department had the same or even better odds as a man applying to the English department. And if she applied to the engineering, she had the same or better odds as a man applying to the engineering. So but because women chose harder departments to get into, their overall admission rate was lower. So the aggregate statistic, 35 versus 44%, suggested discrimination. The disaggregated data showed no discrimination at all. So the aggregate reversed the truth. This is Simpson's paradox. So think about what would have happened if the researchers had just looked at the aggregate data. Berkeley would have been accused wrongly of discriminating against women. Administrators might have been fired. Policies might have changed based on a complete misunderstanding. Real harm would have been done to innocent people. But the statistics weren't lying. The 35 versus 44% was mathematically correct. But the interpretation that this difference meant discrimination was exactly backwards. Okay? So there is no simple algorithm for detecting Simpson's paradox. You have to think about the structure for your data. Are there subgroups that should be analyzed separately? Is the aggregate hiding important heterogeneity? Could the conclusion reverse if you disaggregated? So the lesson is, don't just look at the aggregates, examine the disaggregated patterns, examine the individual parts of it. Okay? Check whether your conclusions hold up when you break the data apart. All right, so let me step back and kind of circle back to the beginning. What is typical? In central tendency, we're looking at what is typical. So what's normal? What represents the distribution? But the thing is, there's no objective answer to this question. Typical is not a fact waiting to be discovered out there in the world. It's a concept that we impose on data, and different definitions of typical give different answers. So what's a typical American? What's a typical American by income? That's one answer, maybe 50,000. A typical American by age, that's maybe 38. Typical American by geography, different again, maybe suburban. Typical American by education, by politics, by religion, each gives a different answer. There's no single typical American. There are many typicalities, each defined differently, each answering a different question. And even within a single dimension, the answer depends on which measure you choose. Typical income by mean, by median, by mode, 3 different numbers. So this isn't statistics failing. This is this is reflecting reality, that reality is complex. Reality is multidimensional, okay? People differ in countless ways. Any summary statistic loses information. As you summarize, you lose information. So a single number can't capture the richness of a distribution. The question isn't what is the true central tendency. That question has no answer. The right question is what summary is most useful for my purposes. Different purposes require different summaries. If you want to minimize prediction errors, you use the mean. If you want the 50th percentile, you use the median. If you want the most likely specific value, use the mode. And I know you don't understand all those, but you get the idea. And if you want to communicate honestly to policymakers, to the public, you use whichever measure is most representative, and you're transparent about what you're doing and why. Every summary serves a purpose. There's no neutral objective measure of center that sort of transcends everything. And that means you need to be aware of your choices. You need to be transparent about them. You need to be honest about what you're hiding as well as what you're showing. Okay? So some measures really are more appropriate for some purposes. Okay? And the choice of measure is a human choice with consequences, and that requires judgment. Okay? So a competent statistician knows the formulas, but a wise statistician knows when to apply each one and has the honesty to acknowledge the limitations of whatever statistic that they're using. Okay. So let's finish this off by sort of giving a little preview of what's coming next. Okay, so there is a fundamental limitation of everything that we've discussed today. Central tendency tells you where the center of your distribution lies. Okay, it does not tell you how spread out the data is around that center, and this matters enormously. So I mentioned this early, but let me develop it more fully. So you remember this example, Class A, the mean exam score was 75, and all the scores clustered between 72 to 78. The mean of 75 represented everyone pretty well. The students were clustered tightly together. Okay, everybody was pretty similar. But Class B, it was bimodal, so the mean score was still 75, but the individual scores ranged from 50 to 100. Half of the class scored around 55, half scored around 95. The mean of 75 represented nobody. No one scored anywhere near 75. Same mean, completely different situations, okay? So if all you knew was the mean, you'd think these classes were identical, but they require completely different interventions. So what's missing? The central tendency tells you where the center is. It doesn't tell you how far do things spread from the center, how different are individual observations from each other, how much variation exists in the data. Is the distribution tight and clustered or spread out and dispersed? It's like having a map that shows you where the center of a city is, but not how far the city extends, so you know what you're aiming for, but not how far you have to travel to get there. Okay, so central tendency and variability together describe a distribution. Variability is what's showing you how wide the city is. So you need central tendency, but we also need variability, which we'll be talking about. Central tendency tells you where things cluster at the center. Variability tells you how spread out they are, the dispersion. So you need both for a complete picture. Central tendency alone is incomplete, sometimes dangerously so, as the Class B example shows. So next time, we're going to talk about variability. The range, the variance, the standard deviation, and what it means for data to be tightly clustered versus widely dispersed. And that is going to complete the basic descriptive toolkit for statistics. Okay, so next time we finish central tendency today, next time we'll be doing variability. Okay, so that's it for today. Do your reading, practice, calculating the means, medians, and mode until the process is automatic, and think about what typical really means, and be honest about what you find. And I will see you in the next class.